As a software engineer, chances are you've crossed paths with MongoDB at some point, whether you're building an app for millions of users or just figuring out your side hustle. It's the most popular non-relational database. MongoDB is intuitive and incredibly easy for development teams to use. Now, with MongoDB Atlas, you can take advantage of MongoDB's flexible document data model as a fully automated cloud service. MongoDB Atlas handles all the costly database operations and admin tasks that you'd rather not spend time on, like security, high availability, data recovery, monitoring, and elastic scaling. Try MongoDB Atlas for free today. Visit www.mongodb.com/cloud to learn more. That's mongodb.com/cloud. Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and today I'm talking with Ben Hilburn, the president of the GNU Radio project, and we are both very excited about software-defined radio. And you found me because I was geeking out about how great it is.
Yeah, I spend a lot of time geeking out about software radio on Twitter, so I was very excited to see you do the same.
Yeah, whenever someone discovers a new kind of, I'm calling it a new hello world, because we spend all this time teaching people how to do hello world by them, outputting a text to a console. And then we wonder why is this 13-year-old child not excited about software? We just said hello world on a console. Isn't that enough for you?
Yeah.
So now I'm thinking maybe I can teach them by plucking signals off of the electromagnetic spectrum.
Yeah, it really is an incredible demonstration of technology. It's something you like when you do it, you immediately feel a huge sense of achievement.
Mm-hmm. So I have to go and talk to a bunch of kids tomorrow. I'm going to talk to 50 kids between 11 and 15. And I think they have probably talked about the electromagnetic spectrum, or at least they talked about visible light. And I wanted to understand that. So there's this spectrum, there's electromagnetic waves in this wide range of frequencies. And on the one end, you get frequencies that turn you into the Hulk, right?
Yeah.
And on the other end, you're looking at black holes. Talk to me about the spectrum and what's in there.
Right. Yeah. So as you said, electromagnetic spectrum varies from what we would call, or 0 hertz would call DC sometimes, all the way up to, there's no end to it, right? But to give you some example, optical light is in the hundreds of terahertz, whereas broadcast FM radio, that you would listen to in your car, for example, is in the high tens, low hundreds of megahertz. So several orders of magnitude below that. So it's really just this huge range, and it contains everything from the emissions from black holes to the signal that your car stereo receives.
Mm-hmm. Is Wi-Fi in there? Is Bluetooth
it
in
is.
there?
Yes. So for the tech focused out there, it's called the ISM bands, and those are, what that means is those are bands that you're allowed to transmit in without having a license. So there's most bands are protected. So Verizon, for example, has to tell the FCC, hey, we're going to put up a cellular base station and we're going to transmit in this band, and we expect all of our users to be, at frequency X, and they have to get a license for that. Well, obviously, you, Scott Hanselman, did not ask the FCC for a license to operate your Wi-Fi router. And that's because your Wi-Fi router works in this unlicensed ISM band. And right now, the Wi-Fi is typically around 2.4 gigahertz or 5.8 gigahertz, which are two of the most widely used ISM bands.
And so this is effectively real estate, right? Just like we have the world, and my dad always says, invest in land because they're not making any more of it. Are they making any more of this real estate?
No. So for decades now, for a couple of decades now, sort of the wireless world has been freaking out about what's called the spectrum crunch, or spectrum scarcity, which is everyone's running out of spectrum, right? So the problem with extreme, so different this is, let me know if I sort of dive way too deep here.
No, I'll stop you because
okay.
I'm right there with you, but I get the idea that there's this range.
Right.
And I know that there's a lot of stuff there. And I'm thinking about what's the IPv6 of the electromagnetic spectrum? We're about to run out of IP addresses. Let's fix it. What do we do when we run out of light?
So the first key thing to understand is why the frequency matters. And it's because different frequencies have different characteristics in terms of propagation. And what I mean by that is when you emit a signal at a certain frequency, how it gets from where you transmitted it to a receiver somewhere else is very different depending on the frequency at which it exists. So as an example, something at what we would consider to be a relatively low frequency, say 10 megahertz. Right. Those low frequencies can they go very, very long distances. So, sometimes you hear about amateur radio operators who are bouncing signals off of the moon, and then to get them to the other side of the world to talk to somebody on the opposite side of the world. You can do that with low frequencies. You cannot do that with much higher frequencies because those higher frequencies experience what we call attenuation, which is basically loss, power loss in the signal as it moves through space.
Whoa! I just had a moment. So I have a 2.4 gigahertz and a 5 gigahertz SSID Wi-Fi channel, and 2.4 is, not super high bandwidth, but it definitely goes out into my backyard. And the 5 gigahertz one is really, really great and high speed, but barely makes it, to the window.
That's exactly right. And that's exactly what you're seeing is, your 5.8 gigahertz band, it's twice the frequency of your 2.4 gigahertz band, and it does not propagate as far. And so what we've seen is with our existing technology, we are constrained to within a certain band of wireless frequencies that our consumer electronic devices can work at. So there's two ways to get more spectrum. Obviously, we can't invent more spectrum, right? It is a thing. It exists. It's
well, you can't make any more. You can't make any more numbers, but you can add a lot of decimal points.
Exactly right. So it's a fundamental property of physics. Actually, it's one of the 4 fundamental forces of the universe. So 2 ways to get more spectrum is you either use what we have access to more efficiently, or we go up in frequency. So both of those are technology problems. And it's everything from faster processors and more accurate what we call analog to digital converters or digital analog converters.
So they're able to pluck it out at a more fine grain, like tweezers.
That's exactly right. All the way up to like applying artificial intelligence, for example, to figure out, okay, how can I more effectively share this spectrum with another user?
Interesting. It makes me think about how I just recently upgraded from 100 megabit to gigabit Ethernet, but it's still going over the same coax cable, and that's the same coax cable that just brought me like regular old analog TV 20 years ago or 30 years ago. And I'm trying to understand, the cable's the same cable. It's still the same thing, but they've shoved a lot more information in that little pipe.
Yeah, and what's really cool is all of the physical concepts that sort of define how your wireless signal works, like your wireless Wi-Fi signal. It's the same thing in that twisted pair coax. They're all this.
What is it?
Yeah, we call all of that RF actually. RF being radio frequency. So the internet connection you're getting through your cable is an RF technology, and your Wi-Fi router is also an RF technology. Just that one happens to be wired and one happens to be wireless.
Really? Okay. So these are all just vibrations of the electromagnetic radiation, whether it be through the air or physically on a piece of wire.
That's exactly right. And vibrations is it's a fairly good approximation, right? It's like the deeper dive would be a magnetic field induces an electric field, which induces a magnetic field. I'm going to
go ahead and go with vibrations.
Yeah.
Or waves. Yeah, indeed.
Yeah, absolutely.
Now, when you look at this, at least when we look at this in school during the 10 minutes that they talk to us about this in high school, they always like to talk about the visible spectrum. And, depending on what bar chart they ended up showing you, they always say, look how small it is. Look, this is what's visible. And this is all the other stuff. Can I take a software-defined radio and see light, or does an SDR only allow me to see certain parts of this spectrum?
So it would certainly be possible for someone to build a software-defined radio that worked at optical frequencies. And that kind of that kind of exists in the form of like fiber optic transmissions, for example. But typically, when we talk about SDR, we're talking about sort of commercial off-the-shelf software radio products, which are usually between 6 gigahertz and below, whereas optical light again is at hundreds of terahertz. So you can go on Amazon and spend $20 or $25 and buy a low cost software radio receiver. You're not going to find something like that works at optical frequencies.
Okay. So I went to Amazon and I bought one for $19, and it's so small, it basically just looks like an antenna and a USB thing. Like it's almost so small that it feels like there's just nothing in it but air.
Yeah.
But then when I looked for software-defined radio, I found ones that were $300 boxes, $500 boxes, varying levels of complexity. What is the difference between the $19 one or the one that just fits into like it's in the USB stick itself?
Yeah, so there are. I probably know exactly the device you're talking about, and kind of to your point, you can buy software radios that are $20, and you can buy software radios that are in the millions of dollars.
Oh wow!
And so the difference is really in the fundamental radio capability that it provides. So the device that you have, for example, is receive only; it cannot transmit.
True.
It is a single antenna only, so you can't benefit from multiple antennas or multiple channels. The device you have, I believe, is probably an 8-bit ADC. What we mean by that is the analog to digital converter that is listening to the electromagnetic wave that hits your antenna and turning it into a voltage, right? So, or a digital number that represents a voltage. So we're going from analog information to digital bits. It can only represent that voltage with 8 bits of precision. Whereas if you were to spend a lot more money on a radio, you might get something that's producing that number with 24 bits of precision.
Okay.
So there's all kinds of power amplifiers and that sort of thing that go into making the difference between a $20 receiver and a $100,000 receiver.
I see. Okay, so then when I go and I was listening to the news, like the National Public Radio, and with 8 bits, I can go and get 250, a number from 0 to 255 effectively. And with 24-bit, we're going off into space. We have just incredible amounts of, 16 million. The range is insane from an unsigned integer perspective.
Yeah,
the detail is very much increased. That's
exactly right. And so that directly impacts the type of information you're able to reconstruct. So let's think about your voice. Okay. So let's say, Scott, I'm going to take your voice and I'm going to quantize it. What I mean by that is I'm going to take your voice and define digital values that describe your voice. So when you speak really lowly, I'm going to say that's 10. When you speak really high, I'll say that's the max. That's 255, right? Giving myself 8 bits here, right? So, but obviously your real voice is a continuous function, right? There's not these individual steps between levels. So there's loss of information here because I can't accurately represent the entire range of your voice. But let's say I take that from 8 bits to 10 bits. Now I have, 1,024 levels. Now I can represent more information. And so that same concept applies to communication systems.
Okay. So you mentioned that the radio is small, it's receive only, but still with this little $20 thing, I was able to do a whole lot. Now I did find that when I tried to listen to quote unquote the radio, and by that I mean FM radio, I did have to kind of move it around. It felt like the old days where I was holding the antenna up in the air to make sure I got a good signal. I wasn't picking up kind of like a lot without having to do a little bit of work. That's just based on the size of the antenna?
So there's a lot of factors at play there. And I'm not exaggerating when I say many, many graduate theses and dissertations have been written about this topic. And so that's everything from when a radio signal is transmitted, there's not a single path that it takes to a receiver, right? It's bouncing off buildings and it's moving through trees and it gets slowed down, going through windows. So, depending on how you move your antenna around, the signals that are incident upon your antenna vary widely. And that actually is even more affected by the frequency at which you're operating, because the wavelength of a very high frequency signal, and by wavelength, I mean radio signals, as they're moving through space, they actually can be, they have some amount of wavelength before the period repeats itself. So if you think about a really high signal, you can think of it as like scribbling really, really quickly up and down. Whereas a low frequency signal is sort of going up and down really slowly as it's going through space. And so as you move your antenna around, you're going to see different parts of a very high frequency signal differently than you would see parts of a very low frequency signal. So there's so much complexity to something as simple as just moving your antenna around and seeing how it affects the reception of the signal that you care about.
It's interesting. I was driving yesterday in Seattle, and I was using my GPS, and I'm in downtown Seattle. And if you've been down there, you know that the streets are quite narrow and the buildings are quite tall. And I'm driving and doing my thing, and suddenly on the GPS, my car moved over 2 streets. And I was like, I guess I'm not where I thought I was. Is the signal, the frequency of the GPS bouncing off buildings, and then it just bounced in a different way, and I found myself elsewhere?
Yeah, so it's funny because GPS, the way that particular what we would call waveform is designed, is not terribly robust to working well in urban environments. It doesn't do well going through buildings. It bounces in weird ways. It can't propagate through concrete. So that's why when you're in a parking garage, you get that GPS signal lost message from your phone. And that's exactly what you described is exactly right. We would call that multipath, where that GPS signal is bouncing off the urban environment, and what you are receiving confuses the radio. It decodes the information and just says, okay, well, I'm doing the best I can, but you're not actually getting what you should be.
Right. And of course, you're picking it up from multiple satellites, so it's probably internally voting on what it thinks is going on. And when they all agree, it gives you a general sense of where you are. When they all disagree, it's like, well, good luck. Yeah. Good luck finding your way around Seattle.
Yeah, GPS is inherently, the way that GPS works is actually a time-based system, right? The GPS satellites, all they're doing is broadcasting their time, their instantaneous time. So when you get into scenarios like that, it sort of falls apart quickly.
Yeah. Your code is powerful, and so are you. And when you consider the reach of your code, it's clear that to deliver quality code, you must also deliver secure code. So where can you start? A first step is educating yourself on basic secure coding principles and beginning to put these principles into practice every day. Vericode's Secure Coding Toolkit is your go-to resource for all your secure coding needs. The benefits of the toolkit include learning best practices for secure coding, understanding how to secure your DevOps environments, and learning to combat the most common software vulnerabilities. Stay secure and download this valuable asset today at veracode.com/toolkit. That's VERA code.com/toolkit. So I got this little radio, and I can go and install the software for it. And there's lots of different pieces of software for it. And as people go and explore this, a lot of them will find or think that they have to pay, they have to buy a package for this, but they don't necessarily have to buy a package once they've got their radio.
Yeah, that's right. So the software radio community has really grown up around open source software. I realize that it can feel silly to talk about software radio and using software with it versus the hardware device itself. It's probably worth real quickly just clarifying that by software radio, we mean a hardware device that is controlled and used by software.
Okay, so there's no knob on my device. That's right.
So the way I like to describe this, and I realize I'm sort of deviating from your question a little bit.
No, please.
So my favorite analogy for this is if you sort of think back to the way computers were when they were first created in the 40s, in the 1940s, where in order to represent some computation, a programmer would literally, flip switches and plug wires into various ports to create an electrical circuit that represented the math that needed to get done, right? And that has, as computing has evolved, we're at the point now where instead of having algorithms defined in hardware, we have general purpose processors that we then tell what to do with software. And that's exactly the same thing that's happened with software radio. So many decades ago, you would build a piece of, or an electrical circuit that did some radio function, and it would do that one radio function. Well, now we build general purpose radio hardware, and we tell it what to do and interact with it through software.
Now, I'm just exploring this space. So the things that I was the most interested in were two things, and I thought they were kind of my two fun hello worlds. The first one was to just listen to the radio, to plug it in and put in like my favorite radio station at 91.5. I believe that's megahertz, right? That's where FM is.
That's right.
And then I can see it. And what was interesting was when I did that, I'm here in Portland, so 91.5 is National Public Radio. I could see the neighbor stations for the first time in my life, literally next door. Like I know that they're next door. I intellectualize that they're next door, but seeing the kind of the bell curve and then an empty space and then the other stations, one of them was rock music and one of them was jazz, and they looked different. Like I didn't listen to them, but I could tell that that's the rock station.
Yeah, that is. So we, in the radio community, especially in the open source world, we generally consider building an FM radio receiver to be our equivalent of a hello world.
Good.
You did exactly what we would have told you had you asked us.
Excellent.
And yeah, exactly what you're describing. So what you're describing is visualizing the frequency domain, right? Because what you saw is not how right. It's not how signals quote unquote look in the air.
Indeed.
Right? And so what you were looking at was a visualization of the power in the electromagnetic spectrum across different frequencies. And so you could see, those exactly as you described, those radio stations positioned around, and the power levels going up and down in frequency as your receiver saw things happening. And what's amazing about that to me is, actually, Richard Feynman has a really great talk about just how incredible electromagnetic spectrum is, because it's just everywhere. It permeates everything. It's kind of like the Force, right? It is absolutely everywhere all the time, and things are bouncing everywhere. And the air around you is filled with information. And normally as a human, we do not have the sensors, quote unquote, to be able to observe that. But using this software radio technology and open source software, you're able to observe it and interact with it, and actually manipulate one of the four fundamental forces of the universe. And that's just incredible, I think.
Why do people, not to get too off topic, but why do people worry about whether it be the microwave oven in the 80s? Everyone was like, stay away from the microwave will give you cancer, or don't put the cell phone to your head. There are dangerous electromagnetic frequencies, but are not the ones that we spend time in and hold near our heads and sleep next to ones that are probably not going to kill us?
Yeah. So this is the realm of, there's all kinds of conspiracy theories and real science and pseudoscience and, unfinished studies. There is a scientifically accepted health, sort of health studies about this. And the key thing is all of the frequencies that we're interacting with, or rather all of the frequencies that, we sort of blindly transmit out into the open, like, FM broadcast radio and Wi-Fi and, that sort of thing. That's non-ionizing radiation. So what we care about in terms of health is ionizing radiation. What we mean by that is ionizing radiation is radiation that when it, hits the atoms in your body, it can change, it'll, affect the electrons of those atoms. And that requires a certain energy level, within that radiation. And so all of the signals that we're talking about, don't have that energy level. They can't affect the atoms in your body.
Okay, so when we say ionization, to use not an analogy, but oversimplifying, it's like these are ones that are energetic enough to cause trouble, and these ones are ones that they're just passing through. And honestly, whether you decide to have Wi-Fi in your house or not, you're going to have these things running through your body all the time anyway. So,
that's what you just said is how I wished I had described it.
Now, the next step was I was at 91.5 megahertz, and then I have an insulin pump, and I wrote an article about this, and there's also a wonderful article that I'll make sure I put in the show notes by Pete Schwamb, who used a software-defined radio to decode what was happening at 915 megahertz, which happens to be where my insulin pump does its radio frequency communication. And what I haven't succeeded in doing this, but I want to figure out how to get the ones and zeros off of that wire, basically see the packets going by. I've got it to the point where I plug the software-defined radio in. I can initiate communication with the insulin pump. I can see lights blinking on the pump, and I can see the frequencies and the powers change at that frequency, but I don't know how to get from there to ones and zeros. What's that leap?
Yeah, so that's a really cool question. And I'll also go ahead and take the second to point out that 915 megahertz is the third most popular ISM band. So
it's the sub-gigahertz band. Like I've also found out that my garage door is there too, which was surprising.
That's right. It's also where, if you remember, back in the 90s and early 2000s, everyone had wireless, handheld landline phones. And that's where those phones operated.
I remember those were so bad. They did not work well at all.
Really terrible. But to answer your actual question, so what's interesting about what you just described is they're actually two fundamentally different radio technologies. So what I mean by that, and so you're actually describing a split between analog modulation and digital modulation. So when you listen to your FM broadcast radio, right, that your hello world, what that signal is, what FM radio is frequency modulation. And to give the sort of the simplest response, if you think about, when you talk, right, and you see, like a wave that represents your voice, right?
Right. And if I'm loud, it's really tall.
Right. So what analog modulations are is they don't attempt to turn that into ones and zeros. It just takes that raw signal that represents information, in this case your voice, what we call mixes, which basically means put it up at a certain frequency. So it takes your voice, which is at hundreds of kilohertz, multiplies it up to 91.5 megahertz and transmits it. So there is no digital information. It actually is your voice just multiplied up. So it's such a high frequency, you can't, quote unquote, listen to it without a radio. What you described, though, at the insulin pump, now I have to say I have no familiarity with the particular device you're talking about, but assuming it's a digital modulation, it's entirely different. So what it's doing is it's taking the information it wants to transmit, and it actually is looking at it in terms of ones and zeros, turning that into packets, right, and then modulating those packets and transmitting them. So when you listen to an analog modulation, you don't ever have to, the only reason you would put it into ones and zeros really is so that you could do something with it on your computer. But if you had the right equipment, you could actually just go basically directly from antenna to speaker. Because there is no ones and zeros computation necessary.
Okay, so my radio is not making a wave file out of bits. It's going analog, and it's like there's no conversion. Here, listen to it.
Yeah,
versus making it.
Yeah, you certainly couldn't do that. But what your insulin pump, for example, that actually is working with digital information, and so suddenly there's more complexity, right? So now we care about things like how big is a packet? What is the header information on this packet? What if one of the bits gets flipped through the air? Do I have error correction so that I'm robust to that, right? So all these additional layers of complexity as we sort of advance that modulation.
Yeah, it's really fascinating. So if I can paraphrase what you're saying and then add on how the insulin pump works, when I'm listening to the radio, like you said, it's analog, and there's amplitude there where the power is giving me information, but not turning it into a number. But with the insulin pump, they're using what's called frequency shift keying. So rather than going, and again, oversimplifying, up and down, it's going kind of left and right. It's like, okay, I'm going to stand a little bit to the left, that'll be 0. And I'm going to stand a little bit to the right, that'll be 1. And it's dancing around that center frequency, expressing the higher frequency as a 1 and the lower frequency as a 0. And then to go and solve the problem of, did I miss something? It actually encodes one bit with 2 bits. It uses a thing called Manchester encoding. So these are all ways to work around, it sounds to me like, basically the electromagnetic spectrum wasn't designed to shove bits around. So we're going to figure out how to put them in envelopes and put them in preambles and put them in headers and shove them through this fundamental force of the universe.
That's exactly right. Yeah, the wire. So working at RF, which working at radio frequency, whether it's wired or wireless. Now, wired channels tend to be a lot easier to deal with, but it's very hard, right? It's kind of funny because the longer that I've been in this field, the more incredible it is to me that any of this works at all. You sort of all the time.
You've just described all computers, though.
Sort of all the time, you learn about like one more thing, and it's like one more thing that these radios have to deal with to get a bit from the transmitter to receiver. And you're like, how did anyone ever make this work? How does and that's exactly right. Every single impairment, has to be dealt with in some way for a communication system to work.
So people should go to Amazon, whether you're an adult or a kid, or an adult who has a kid or knows a kid, and start with a kit. Get an SD radio, get an SDR. They're very inexpensive. They're super fun to play with. You can start at GNU Radio, gnuradio.org. And also it's worth pointing out that you're having a conference in Alabama in September. So September 16th to the 20th in 2019, the GNU Radio conference is happening.
Yes, that's right. So we have a yearly conference. We've been doing it since 2011. So this will be our 9th year. And, it's been really incredible. When we first started out, we were, 40 people sort of crammed into a classroom at UPenn. And now, we have several hundred that come together every year from all over the world. And, it's everyone from, a hobbyist or a student just learning about radio, or, they're just interested in hardware, or they're interested in math or physics, all the way up to people who've been building these radios for decades. So we have a really incredible array of people. It's an incredible place to meet the community and learn.
Fantastic. And also, as you famously said, that of all of the 4 fundamental forces of the universe, weak nuclear force, gravity, strong nuclear force, and electromagnetic, only one is safe to manipulate from home. So we should all get an SDR and get involved in software-defined radio. Yeah,
the community is very welcoming, and software radio can be overwhelming. There's so much to it, but it's also incredibly rewarding, and there's many people all over the world that all want to figure out this together and do cool things.
Well, thank you so much, Ben Hilburn, for chatting with me today.
Yeah, this has been really great. Thanks for having me, Scott.
This has been another episode of Hansel Minutes, and we'll see you again next week.